Good afternoon to those in person and those on Zoom. And welcome to the special edition of the Warren Seminar Series. My name is Joe Labus, Department Head of Civil, Environmental, and Geoengineering. Today's seminar is special because it features the Catherine and Arthur Sehlin Memorial Lecture, which will be delivered by Ron Klemencic. Before I introduce Ron, I will provide some background on the lecture. The Catherine and Arthur Sehlin Memorial Lecture is supported by a fund established in 1986 by the Sehlin family to reflect the values expressed by Catherine and Arthur Sehlin in their volunteer and professional activities. Catherine Sehlin's career as a volunteer and community organizer spanned 35 years. She served as chair of the Governor's Council on Aging and twice represented the state of Minnesota at a White House Conference on Aging. She also founded Opportunity Workshop, a nonprofit organization serving developmentally disabled adults. Arthur Sehlin built the Industrial Construction Corporation into one of the top bridge construction firms in the country. The company branched out into steel construction after merging with Allied Steel of Chicago. The firm participated in construction, repair, and demolition of more bridges on the Mississippi River than any company in the United States. At the time of Mr. Sehlin's death, the company was beginning a major renovation of the Golden Gate Bridge. In addition to his professional activities, Mr. Sehlin joined his wife in working for many humanitarian causes. In recognition of the Sehlins' varied interests, the Sehlin Lecture Series alternates between the Department of Civil, Environmental, and Geoengineering and the School of Social Work. The commitment of the Sehlins to education and their pride in the University of Minnesota inspired the creation of the series. Please join me in thanking the representatives of the Sehlin family who are participating through Zoom. It is now my honor to introduce the 2021 Sehlin Lecturer, Mr. Ron Klemencic. Ron is chairman and CEO of Magnusson Klemencic Associates, a structural and civil engineering firm with offices in Seattle and Chicago. Ron earned his degrees in civil engineering, bachelor's from Purdue University, and master's with a structural engineering emphasis from the University of California, Berkeley. Ron has worked in 29 states, 25 countries, on projects up to 8 million square feet in area and 112 stories tall. He has pioneered the application of performance-based seismic design for tall buildings and co-authored the Tall Buildings Initiative guidelines. Ron's most recent innovation, a cutting-edge composite steel frame, is the result of a 15-year research project that is now being implemented at Rainier Square redevelopment in Seattle. Ron's work has been recognized by numerous awards, but I'll mention only two, both in 2020. The American Society of Civil Engineers Distinguished Member and being elected into the National Academy of Engineering. Ron is one of the leading structural engineers in the United States, and it is fitting that he is delivering the 2021 Sehlin Lecture. Please join me in welcoming Ron Klemencic.
Well, good afternoon, everyone. Joe gave me permission to shed the mask. I hope that's okay. I'm absolutely honored, Kathy, thank you, 30 years in the making, to be invited to come here to be with you today. I got to meet one of my heroes, Ted Galambos, today for the first time. Very cool. I'm hoping to share with you today just kind of a few observations and I'd say things that have driven my career to kind of get where I'm at. It's not all about me, it's more about some ideas that I want to share with you to hopefully inspire some thinking from you. But before I get to that, I want to start with a little story that in 1985, I was a senior at Purdue University, and I sat in a lecture room much like this, and there was a guest speaker who'd been invited in to come and give a lecture then about the design and the construction of the new Kingdome in Seattle, Washington. Kingdome is since gone, but then it was something fantastical. I was blown away. That was the most amazing bit of engineering, the most brilliant engineer I'd ever heard speak. I was so inspired to launch my career into designing buildings of all sorts. This guy's name was Jack Christensen. I didn't know who Jack Christensen was. I didn't know anything about his company. All I knew was that was really cool, and I wanted to do stuff like that. So I launched my career, and I went about my business. And as the kind of winding road would have it, in 1992, so only a short 7 or 8 years later, I joined a firm named Skilling, Helly, Christensen, Robertson. The same Jack Christensen. I kind of earned my stripes. I worked hard. I loved what I did. I was inspired by Jack and John Skilling and Les Robertson and all these people that I had around me, inspiring me to do what I do. And here I am today. Magnusson Klemencic is the next evolution of that same firm. So in particular for the students who are here today, know that you have this amazing opportunity in front of you to use your skill and follow your passion. And in 20 or 30 years, you might own this company and have your name right there. Because it happened for me. Why can't it happen for you? So that's a little bit of a real live story, which it's an amazing thing to just go on that journey. So I have this really ambitious program I'm going to share with you today. The secret to everything. Wow, it's pretty audacious, pretty bold. What I'm hoping you're going to take away from this is that there's 3 things that I've observed in my career that really are, in my view, the secret to everything in terms of me and our company and our practice progressing. There's only kind of 3 simple ingredients. And I hope before this lecture is over that you'll remember just those 3 things and take them away and think, how can I use that in my life? So we're going to get into those 3 things. Well, let's start with first, there's an idea, right? I got to have an idea. And then I need a bag of money. And then I got to have a bunch of smart people to help me make it go. That's it. The secret to everything. The reception will now begin. All right. That's a little bit of a joke. I'm a bit ahead of myself. There's more to the story. So let's get into the story. So let's start with this, right? The sky is blue. And the grass is green. And the speed limit is 55 in some places. Why? Now, these seem like, what are you talking about? I thought this was a structural engineering lecture. Bear with me. But secret number 1 to unleashing possibility is to ask and understand why. Why is something the way it is? Because so much of what we do, in particular in structural engineering, is folklore. Most of it, well, a lot of it, not based on science. A lot of it based on committee negotiations. A lot of it based on, well, this worked, and so let's make it forevermore the thing. Understanding why something is the way it is gives us a basis to question and ask other questions. So here again, the speed limit's 55, or is it 60? Or is it 65, or is it 70? Why? Why are these things the way they are? Well, for structural engineers, we don't care about speed limits. But there are a lot of other things that we do think about and care about. So this is secret number 1, is to ponder the whyness. and dig deep on why. Don't accept it for the way it is, because chances are there's some funny story behind the way it is. I'm going to give you some examples. So let's start with some other interesting things. So in the beginning, right? In the beginning, God said, let there be light. And there was light. And at some point in the history of humanity, down from the mountain came something we call the building code. It was etched in stone, words written by God, never to be violated or you will burn in hell. Right? This is how we go about our business most of the time. Why? It's nonsense. I sit on those code committees. We are far from godlike. Sometimes we're not even that smart. So why do we treat the building code as something that was etched in stone and carried down from the mountain by Moses? Let's not. So let me give you a couple of examples of some of what I'll call folklore, code folklore. It's not necessarily nonsense. It was well intended in its time, but today it's still in practice. So a lot of my work is in the world of seismic engineering. Spent most of my career doing things related to earthquakes. And in the building code, there's this magical value that we use today called R, the response modification factor. And for those old timers in the room, we know before R, there was something that was called R sub W. And before R sub W, there was something that was called K. Okay, these numbers, these magical numbers written in stone from the mountaintop, what are they and why did they come, where did they come from? Why do we have them in the first place? Why? Ask the question. So the truth is they have their birth in the 1940s in San Francisco and Los Angeles, where earthquake engineering was really first starting to come into practice in a really meaningful way. And the engineers there then were struggling with, well, how do we go about our business? How do we design these buildings for these earthquake demands, but do it with the tools that we have and with the techniques that we have at the time? So think about this. This is the 1940s, right? There was no ETABS. There was no SAP. There were slide rules. There was papers and pencils, but there wasn't a lot of the tools that we had today. They were working in a very different environment. And so what they were trying to do, this is a response spectrum for a site, but right, they were trying to do is take the acceleration demands for a design event, a very large event, noting that we're going to allow our building to respond nonlinearly. And as it responds nonlinearly, we're going to take up that energy, the distance between here and here, in this nonlinear response of our building, so we can reduce these forces down to this other lower level, which allows us to design elastically. We can do hand calculations, and we can design our buildings using elastic design techniques. And the difference between here and here, the real earthquake and the make-believe numbers, is R, or K, or what have you. And so what is it? Why is it? It was a tool of convenience. They didn't have the methodologies or the resources or the computational power to go and analyze this directly, so they had to come up with a fudge factor to get here. That's all K is. It's a fudge factor to allow then engineers to design by hand with the tools of the day. This is the 1940s. This is the 2020s. We're still doing it that way. The prescriptive design of the code, that's what we do today. For even our most important buildings, I say hogwash, right? We have changed the way we go about our business. We have stronger computational tools. We have better and deeper methodologies that allow us to get at kind of more rigorously understanding the building performance. So why are we still handcuffed with, oh, my building doesn't fit into the R factor table, so I can't build it? Nonsense. All right. Another example in seismic engineering, and my favorite example, And this is going to sound like I'm being very critical of the building code. That's not the point. The point here, again, remember, is why. Why does this thing exist? Why does R exist? If you understand why it exists, now you have an opportunity to question it and have a basis for thinking differently. So my most favorite example, now this is a little dated, it's ASCE 710. But believe me, the same thing exists in 716 that has existed in the code since the 1961 code. There's these magical tables that you see here, just a little excerpt. Special reinforced concrete shear walls are limited to 160 feet in height. Why? Where's the science behind 160 feet? It seems like a really weird number, 160. And it's really precise. Where did this come from? Why is it there, right? This is the question, why? So this is back in the 1990s. I got this bee in my bonnet about like trying to figure that out. Where did this come from? Why is it there? Well, it turns out, this is the true story, it's amazing. In the 1920s in Los Angeles, the city council decided that they didn't want to see the Manhattanization of Los Angeles. Meaning, they didn't want very tall buildings creating these deep canyonous roads with shadows everywhere. They wanted the buildings to be shorter to let the sunlight in and the palm trees grow and be Southern California. So they imposed a height limit of 150 feet in 1920 in Los Angeles. Fast forward to the 1940s when the structural engineers were first starting to think about seismic engineering and thinking about how to craft code provisions that would allow us to design buildings in seismic zones and increasingly taller buildings. They were grappling with height limits for certain systems, in particular load-bearing masonry shear wall buildings. And anecdotally, those buildings had performed very poorly in earthquakes. And so they were aiming to require a more robust design for buildings of significance. And that more robust design was going to be the inclusion of a steel frame in these otherwise masonry shear wall buildings. And so what limit should we choose as the threshold of importance? And there was no science. There was only anecdotal observations. And they decided, well, Los Angeles has this height restriction of 150 feet. So why don't we say for San Francisco, anything taller than 150 feet needs to have a steel frame embedded in it. So well, we will choose 150 feet because it's already a number that's out there. So this is an excerpt from an interview with a really famous structural engineer. But here he's talking about that then in the 1950s, Los Angeles removed their height limit of 13 stories and 150 feet. So at the same time, when the structural engineers were grasping to 150 feet as a number, the city council was abolishing it because they wanted to promote more development in Los Angeles. So there's this kind of intersection of two cars going in opposite directions. But that's where 150 feet came from, was Los Angeles. But that's what the structural engineers started to put into the code. Here's the 13 stories in the code in 1959. And then in 1961, 13 stories or 160 feet. 160 feet. Where did it come from? It's a typo. I'm serious. Today, in ASCE 716, special reinforced concrete structural shear walls are limited to 160 feet. Why? Because of shadows in Los Angeles in the 1920s and a typo in the 1950s. That's why. Science. At its best. I love that story because it's true. I found the committee meeting notes that talked about, what do? We printed all the code books. And they said, we don't know it well enough, leave it alone. Moses from the mountaintop, right? All right, so it turns out structural engineers were really good about setting up hurdles. And we feel really, really compelled to jump one after another, and I'm going to get from this end of the racetrack to that end of the racetrack, and I'm going to jump all those hurdles, which are those building code provisions. Ron Klemencic, I run in that lane. No hurdles, because we ask why. Why is it there? Some stuff's there for a good reason. I'm not saying it's all bad. But I'm saying don't accept it just because it's written in the code book that it's like the thing and it has to be, because so much of it's not. Those are my two favorite examples. So let's talk about a little bit more about seismic engineering. In seismic engineering, we have these performance levels we try and achieve, right? From operational to collapse prevention, depending on the level of the ground motion that is impacting our building. And in San Francisco, this sort of thing actually really happened. Buildings do collapse. We try and not have this happen. This is the framework of our code. Understanding what's the code's objective. We're trying to prevent this. How do we prevent this? Well, you can prevent this by a whole bunch of prescriptive rules that you dutifully follow, and you hope that you achieve that outcome. But do you really know? Or you can more rigorously go about your business, do the analytics, do the physics, do the math, and really rigorously interrogate your design to know. We have the tools today to do that. Why don't we do it? We should. We do it more regularly. But in wind engineering today, for the maximum wind event in Miami, it's a hurricane with 185 mile an hour wind. For that wind, we design elastically. Why? For an earthquake that happens one time every 2,000 years, our threshold of acceptance is collapse prevention. We have lots of damage. The building is at incipient collapse, but the people got out, they're safe, but the building's highly damaged. Yet under a wind event that happens one time every 2,000 years, nothing can happen. No yielding, no cracking, no nothing. Why? Preponderance. Interesting question. Fire engineering, right? In fire engineering, we spray fireproof all of these steel beams and columns, and then we put the sprinkler system in. Does anybody know why? Because the code said. Yeah, but outside from the code saying, do you really know why and what each of those measures is trying to accomplish? And if you knew why, might you go about your business somehow differently? So again, why? Ask yourself in your daily work each one of these things. All right, so that's number one. Enough examples of number one. Why, right? So we're going to move on to number two.
He's our broker. He helps me capture all our money.
Can you pay him?
Of course.
How much?
I don't know exactly.
What if you're not happy? Does he have to pay you back?
Nope.
Why not?
It doesn't work that way.
Why not?
Are you asking enough questions about the way your wealth is managed? Wealth management at Charles Schwab.
So secret number two is not Charles Schwab, and it's not money management, right? But it was captured by the voice of a little kid. He asked, why not? That's secret number two. If you can get past hurdle and secret number one and understand why is it there, now you have a basis to ask this question and ask it really thoughtfully. Why not? Why not do it differently? Why not take a different approach? So, in the world of tall buildings that we're designing today in San Francisco and Los Angeles, in Minneapolis and Chicago and Miami, what have you, in the world that we're designing today, why not take a different approach? We have the tools. We have incredible computing power at our fingertips. We have a really robust understanding about all types of performance of parts and pieces of buildings. And when we're designing these more exotic structural systems that don't fit into any prescriptive description in the code, because they don't, Why not take a different approach? Why are we trying to jam these buildings into that prescriptive language and force it to be something it doesn't want to be? So performance-based design was invented for exactly that, right? This is the famous table that's been around for years and years, but it can be applied to anything. This is for earthquakes, but earthquakes of different magnitudes from 25 years to 2,500 years, so different demand levels. And let's say the different demand levels of any type: seismic, wind, fire, blast, tsunami, you name it, locusts. Pick your hazard, right? Demand level and performance level. It's just that simple. I was telling a story earlier today. One of my professors in graduate school was Vitamo Bertero, brilliant structural engineer, very, very passionate, very motivational. He taught a class called Limit States Design. Years later, I was designing a building and he was reviewing the building and he didn't like my design. And he was pounding on the table, "I do not like this design." And I said, "Professor Bertero, with all due respect, I'm just doing my homework assignment. This is a limit states design approach. We're calling it performance-based design, but that's what it is." And he took a step back and he thought, not of approval. And we got along famously after that. But the whole point of this diagram, right, is this has been around for decades in seismic engineering. Let's adapt a similar kind of train of thought to other hazards. And we have the tools. In seismic engineering, we can take a simple 2D frame, subject it to a ground motion, and understand the nonlinear behavior of that 2D frame. We can do this in 3D easily. We got all kinds of tools to do this. But we can define ground motions, we can mine ground motions from databases, and we can interrogate our buildings to any number of hazards that we want to with real rigorous analytical techniques, and we can better understand how our building's going to perform. Why not? This is back to the hurdles, right? Are we going to jump over all the prescriptive rules in the code, or we're going to run in a lane over here where there's nothing in our way and we go fast, we get to the same finish line, only much better and much faster. But we use science and math and first principles and the tools available to us. Resultant comes out things like this. The Tall Buildings Initiative we wrote a number of years ago, we being a group of people. It was a consensus document amongst a bunch of practitioners and academic researchers to define a new methodology for seismic design of tall buildings. This is the state of practice today. It is now the standard of care on the west coast of the United States and in other places around the world that use our guidelines as their basis of practice, like in Chile or in the Philippines or in the Middle East. These guidelines have spread worldwide, and it really opens the door beyond prescriptive design into the world of performance-based design and more rigorous engineering methodologies. So we ask the question, well, why not? We have all these tools, we have the knowledge, why not do it? So we are. Fantastic kind of a success story. So back to my wind proposition or question. The question of why for a 2,000-year return period wind, why can't I allow even a modest amount of yielding in my building? In fact, it could be a good thing. Just a modest amount of nonlinear behavior does a lot in terms of absorbing energy. And we have ability to kind of tune the system to behave in a way that we can control and we want to achieve, as opposed to hope to achieve. So the good news is today we have the tools to do this thing. Right? We have the tools to do linear and nonlinear response time histories for wind. We're in the beginnings of this adventure. We've been practicing performance-based seismic design for 25 years. Last year, is there a date on this? No. Last year we published this. Who's we? ASCE, SEI, the Pankow Foundation. We published, a group of people got together, we wrote these guidelines for performance-based wind design. The whole point is to create a framework that's non-prescriptive, that allows a structural engineer to allow some modest amount of nonlinear response in your structure in extreme wind loading events. And in doing so, You can spin it however you want to spin it. We're going to save money. We're going to make it easier to build. We're going to make it safer for the construction workers because there's less things in the way. Or the greatest thing of today's language, we're reducing embodied carbon. We're doing all of that because that's what this unlocks the door to. So again, why not? Why not do it that way? Why be hamstrung and handcuffed to the old way? Why not think differently? Back to the fire engineering, same question. We asked, why is there spray on fire protection and there's a sprinkler system and we have this 1 hour, 2 hour, 3 hour, 4 hour rating thing? Why? And if you peel that onion back and start to understand why those parts and pieces are there, it opens the door for you to do performance-based fire design, where you're looking at actual loads in the building, the amount of combustible material in the building, creating it as a load case for the structure, and then analyzing the heat transfer in the structure to understand what's going on with the columns and the beams and the slabs and what that heat is actually doing, and then respond to it with a design instead of not responding to it at all and just spray it with monocoat, because then I don't have to think about it. The state of practice is moving in this direction slowly. This is frightening to a lot of structural engineers because they don't teach us this in school. Well, they're starting to. There's a few schools that are starting to teach fire design as a structural engineering course. I look at it as fire, it's a heat load case. It's nothing more. It's nothing to be more frightened of or less frightened of than an earthquake or a windstorm or a tsunami. We can deal with all of those already. Why don't we deal with heat? That's all it is. And how does your building respond to the heat? And in most oftentimes, what's critical is the cooling. As the building cools, as it has expanded and now it cools, a lot of things move around and there's restraint created, and that's when things break. So how do you go about designing your building for that? And perhaps in doing so, get rid of some of, at least, the spray on fire protection. Why not? Why are we not doing this? We should. We will. I've designed a bunch of heavy timber buildings, mass timber buildings these last few years. One right here in Minneapolis, not far, over by the Twins ballpark. It was the first ever commercial office building in the United States built of mass timber. They're beautiful buildings. They're gorgeous buildings. You go inside, it's, I love this place. From an engineering point of view, they're actually very simple. Everything's a simple span. Wood really doesn't like to cantilever. The spans are really short. It's kind of a yawner from a structural engineering point of view, but they're beautiful. So let's do some. So we're doing a bunch of them around the country. And the one thing that we've learned as we've designed these buildings, right, is the thing that controls the design most often is deflection. And what is the salient parameter for deflection? It's the modulus. It's the modulus of elasticity of the wood. Okay. Why don't we grow a proper forest to build buildings with? I'm talking about genetic engineering. Why don't we grow a tree that has a proper modulus to build a building? Because today what we do is we go out in the forest and we whack down a bunch of trees. Did anybody see or read the book or see the movie Moneyball? Moneyball? It's about the Oakland A's. And the whole premise of the story was that old school baseball was all about visual scouting. I like this kid, let's sign him up. And Moneyball was all about putting science and statistics to work to grade minor league players to put them in the big leagues. And it worked. They transformed baseball because they went from visual grading to scientific grading. Why don't we do that in the wood industry? Because the wood industry is still visually graded. I hosted a meeting a couple of years ago with some forestry people and the timber sawmills and some geneticists. It was a very interesting meeting. The mills don't want to use scientific grading. They want visual grading. Why? Because they can get more crap through the system. It's a commodity and they're trying to sell as much of it as they can. And if they have scientific grading for the wood, it's going to cull out too much of their product and make it non-saleable. They can't get it at the Home Depot. And so they don't want to do it. Even though the geneticists say, oh, we can do it. We can make a better tree. Anyway, I'm kind of going down a rabbit hole. The whole point of this is, why not? Why are we accepting Douglas fir number 2? Right? Because that's what's in the code book, Douglas fir number 2. And we design all our buildings with Douglas fir number 2. And the modulus, and the bearing capacity, and the bending capacity, all the stuff that's in the code. Why not do it different? Why not make a tree? All of this, not all of, much of what you eat has been genetically engineered. The corn and the wheat and the soybeans. It's all been tinkered with to grow more robust crops, faster, healthier, better. Why aren't we doing this for buildings? If we intend to build lots and lots of buildings out of wood in hopes that we might reduce carbon and save the planet, why aren't we growing proper forest to do just that? It takes 40 years to grow a proper tree. We need to start now. Anyways, the geneticists love me. They're like, yeah, let's do it. And the Mills and a bunch of other people said, no. You can't tinker with that. You're like tinkering with Mother Nature, and you can't do that. You're going to get, in fact, some people in Europe tried to do this, and their experimental forest that they planted ended up being burned down by the protesters. We'll just leave it at that. All right, so this is in the why not. So number 1 was why. Got to figure out why. Why is it this way? Then dare, right? Dare to say why not, some other way. And now number 3, kind of the silver bullet. For me, it's the silver bullet that makes it all go. And that is we must collaborate. The death sentence in our industry is proprietary technology. I've come up with a whole bunch of cool stuff that we're doing in buildings, and it's all public domain, intentionally, because I want people to use it. I want everybody to use it, because then maybe it'll get used. This thing, I don't even think it's in this deck. Recently, we've been building this thing called SpeedCore. Yes, and AISC put a name on it, but don't be frightened. It's not patented. There's no trademark. It's free. It's on the internet. All the research we did for 15 years, it's all free. It's all out there. You can do it too. But it's all about collaboration, not only in our own firms, but with our peers. The way we get stuff done in our business and the way we actually change practice is through this kind of grassroots groundswell of enthusiasm of people who want to work together to get it done. It's proven time and time again. Collaboration is the silver bullet. That's how the performance-based seismic design happened. That's how performance-based wind design is happening. That's how performance-based fire design is going to happen. And it's all through various groups of people around the country who are passionate about advancing that technology. And we're doing it together. We're not doing it even though our firms might be competitors for the design of a project. There's a bigger mission here. We're trying to improve practice. So the TBI guidelines were an example of that. That was a collaborative effort. We reinvented how you design and construct reinforced concrete link beams in seismic zones. Very big research effort at UCLA and extended now to Washington State University and University of Cincinnati. High strength rebar is now in the code, up to grade 100. This just didn't happen by chance. This was a group of people who were passionate about wanting to advance this technology, competitors who got together. We got a bucket of money together. We did a bunch of research over 5 or 7 years, and now it's in the code. And so all the high strength rebar, grade 75, grade 80, grade 100, you can do it now, it's in the code. Research, I mentioned SpeedCore, Professor Bowman, Professor Krager. We started 15 years ago in the lab at Purdue, been working with Professor Varma more recently in the lab at Purdue, advancing this technology. All this stuff is public domain. None of it's proprietary, with intent. because we believe that the system is efficient and it's effective, and if more people would use them, it would be great for the world, we think. It is now in the code. The impediment at the moment to building these composite plate shear walls is just habit. Excuse me, the structural engineers practicing by and large today, it's something new. Got to learn something new. It's different. It's not like I can push the button in E-tabs and out poops the design. You can't. You actually got to think about this one. But, sorry, my computer's showing me funny things. The point of it is that this stuff is all public domain with intent. Uh-oh. We have a seizure. Sorry. What happened? Bear with me 1 moment. Do we have the IT guy here? All right, we're going to start over and hope that we solve the problem. Not going to start over, but we're going to just relaunch this thing. Okay, we're back on track. All right, a number of years ago, you might have remembered there was a Northridge earthquake, and there was a precast parking garage that fell down in the Northridge earthquake. As a result of that, there was a huge research project launched, lots of testing done, lots of people got involved, and the precast industry was improved forevermore through that collaborative work. In the world of BIM, there's been a lot of work done. In the world of water, this is all about life cycle. Oh, this is carbon leadership. Sorry, I skipped the water topic, but carbon reduction is a big topic these days, right? This was a collaborative project talking about LCA assessment of buildings, initially started by Skanska, but then joined on by a whole cadre of supporters from the Charles Pankow Foundation to Amazon to Facebook, you name it, all the tech companies got involved to fund the creation of what is now something that's called the EC3 calculator. And if you haven't seen it, I encourage you to go online and look up EC3 calculator. And it's a tool that you can use, again, public domain, that allows you to assess the carbon content of your building via a connection to a national database of EPDs for all kinds of materials. So if you're wanting to do things in embodied carbon, that's a place to go. All right, so we had 1, why, 2, why not, 3, collaborate with your friends and colleagues to make something happen. So now I'm going to go first full circle back to the beginning when we started this conversation. And you'll remember I talked about imagining that maybe you have this idea. But all too often, right, what happens with an idea? Wham! Ran into the brick wall. Can't get her done for whatever reasons. So what do? You'll go back to your office and do the way you always did, the way it's always been done. So I want to paint for you the alternative universe. And the alternative universe is we're going to imagine that we have this idea, whatever the idea is, and I got 20 more to share with you later, maybe at the reception. But we have an idea. And now we need some money. Ha! But lo and behold, I know where to find the money. Send me an email. I'll connect you with the money. There is money to be had, and the number of people willing to fund advancement in structural engineering and building design and construction is growing. So there is money available. And I can assure you there are lots of enthusiastic, in particular enthusiastic young people in our industry who really want to save the planet. And a lot of what we want to do, need to do in our profession right now is to use our tools and use all of our smarts to work toward that end, to saving the planet from carbon. All right, so I mentioned a few, right? The Charles Pankow Foundation is a very big entity that has a big bucket of money. I was so inspired by the Pankow Foundation that we made our own foundation with the same mission in mind, which is to fund research to design and build better buildings. We're not funding the symphony. We're not funding the Children's Hospital. Those are all worthy charities, for sure. I do personally. But as a company, we've decided to take a bucket of our money and put it into research that benefits our clients and our work product directly. Beyond our work, there's a whole bunch of others that are now joining in there. Thornton Thomas said he's got their foundation. ACI created a foundation, so on and so forth. The number is growing. My point being is that the bucket of money is there. Some networking and connecting of dots is required. The Pankow Foundation is very good at that. But if you have an idea worthy that you go, I think I got this idea, I want to float it out to some friends, phone a few friends and phone a few more friends, and then talk to a bunch of people, and then call us. Call the Pankow Foundation. Call the MK Foundation. Call ACI or AISC. Everybody's searching for kind of that next big thing. All right, so now you have it, right? We checked the box. All three. Why? Why not collaborate? And with those things, you can change the world. So, I have given all of you now superpowers. That's all there is. It's that easy. Those are my superpowers. And so you have them now too. You all have superpowers. Remember why? Remember why not? Remember to collaborate. Don't be afraid to call your friend or your competitor and say, I got this idea, what do you think? Because this competitive advantage stuff, yeah, there's something to that, but so I'm going to get booed now, I know, all right? I'm a Green Bay Packer fan. I grew up in Wisconsin. But the coach growing up, right, was Vince Lombardi. And Coach Lombardi had a lot of sayings, kind of like Yogi Berra had a lot of sayings. And Coach Lombardi has this very famous quote that says, I can hand our opponents the playbook, and they still can't beat us. Because when the rubber needs to hit the road, it's really the culture of your company and the culture of who you are as a person that really push it through. So I'm not afraid of this proprietary, non-proprietary stuff. Let's share it all, because it will make it all go better and go faster. So I want you to look in your crystal ball, look in there, and ask yourself, how are you? What are you going to do to change the world? Because you have the superpowers now. There's no excuse. I gave them to you. Thank you all.
Okay, we have time for questions. I need to hand the microphone to you so our guest on Zoom can hear as well. So if there are any questions or comments.
Stunned.
And Mary, let me know if there's anything coming from Zoom.
I gave you no equations. I gave you no physics of science or anything like that. More philosophy.
So excellent. Is this on?
Yeah.
I'm assuming it is. Okay. Excellent presentation, and I mean, I'm pretty enthused by everything you've said. So I work as a structural engineer, and I'm anticipating, my Monday morning next week where I'm sitting in my cube, scratching my chin, saying why. And my project manager walks over and he says, "What are you doing?" And I said, "Well, I'm asking why." And he says, "Well, we don't have the budget for that. We don't have the fee for that. What are you doing? Get back to work." How do you balance, some of your strategies, I guess, with the reality of the profession we work in, specifically as a consultant engineer?
So our company is subjected to the same market constraints that all of you practitioners are subjected to. It's not that we somehow get more money than anybody else. So we're subject to the same pressures. I'd say for our company at least, this is just inherent in our culture of our company, that every day, let me take a little different tact. And this may become controversial, but I'm going to share with you. I'm being open, right? Very direct. So we feel very, very passionately about being together. Our company is 101 years old. It was founded in Seattle. We have really one production office. It's in Seattle with intent. We don't want branch offices everywhere, with intent. And the intent is we want all of our people together to collaborate every day, because we're learning from each other every day, and we're asking that question of why and why not, and every day on every project. It's just part of what we do and how we do. We've been that way for my entire career and well before my career. For 100 years, the company has been that way. And then there was this thing called the pandemic. Don't get me started. There was a period of time where we couldn't work that way. It was killing us, literally killing us. Our effectiveness, our quality, our inspiration was evaporating quickly. And as soon as the state of Washington said, okay, we're open, we were all back to work. Regular hours, Monday to Friday, 9 to 4, core hours, everybody's there. And it's because of the power we know through practice from that collaboration. So there isn't this, we don't have a research group. We don't have people that sit off in the corner, oh, it's Ron's Y think tank. No. It's just part of the culture. And so, I mean, that's great for us, right? Well, okay, I didn't answer your question. How do you deal with that in your practice? Well, you got to start somewhere, right? Why don't you be that kind of maverick that starts asking why? You know, about anything. Why are our notepads got lines on them? Because the lines promote me drawing within them. Why don't I have notepads with no lines? I know it's foolish, but it's that simple. and anyway, okay, I'll stop.
My name is Chuck Nelson, and I used to teach here a long time ago. We designed the excavation that you're in. But in your talk, is that unfortunately I've kind of shifted over more to management, if you work for the Corps of Engineers and a lot of other government agencies, there are these rules about overhead rates and stuff like that. There's fights over them every other procurement. And that's a fact that it is. And now I'd like to ask you, is this a gold mine? Is the industry you're in not doing that?
Not doing...
Not reviewing your charges for the month and say, he did this, did that, it doesn't apply. But we do have non-public contracts sometimes that one could do it, but then you get back to two-way in the firm, and it's even probably some problems with your audits, your federal audits.
Fair enough. So, really good question. Let me just kind of touch on it because it's a very deep subject. Our company doesn't do a lot of federal work. We don't do a lot of government work for exactly that reason. We don't want to be audited. We don't want anyone telling us how much we can charge. And that uncouples our hands to allow us to do a lot of the stuff we get to do, because we're not beholden to filling out some spreadsheet with hours and billing for hours. Our business is built around selling value. And it's with that unshackling that we're able to do a lot of this. Because I agree, if we were shackled to a lot of the audited hourly billing rates and hourly reporting that needs to happen in a lot of government contracts, we couldn't do any of this. And we're fortunate that we don't have that as a company, and it's with intent. We do some amount of government work, but it's very modest in its, if you look at the pie of all of our work, maybe it's 10%. 90% of our work is for commercial, for-profit businesses, and we're selling value.
Hi, Kevin Griebenel, University of Minnesota, 1981. Peace Corps volunteer, Yemen, building reinforced concrete towers. A lot of whys and why nots doing that. Unbelievable experience. My question is, it seems, I actually think I got my best engineering skills of asking why while I was in the School of Architecture. And then when I went over to the School of Engineering, it was, I would say, follow the recipe, or as you put it, follow the code. Comments, or to me, it seems we need to change how we teach.
Perhaps. Did everybody hear that? He was talking about engineering school. Okay, I won't repeat it then. What's the right word I'm looking for here? At the risk of maybe pissing off a few of my very best friends who are professors at a variety of schools around the country, there is a lot of emphasis on teaching the code. And the first thing we do when we hire kids out of school is we try and deprogram them. When I was in school at Purdue, and it wasn't a Purdue thing, I think maybe it was just the way education was then, perhaps, we learned first principles. We learned science and physics and how things worked and why they worked. And I don't remember looking at a code book until maybe second semester of graduate school, except maybe the AISC spec, because you had to go there to look at the beam table. But we weren't taught the code. And I know some of my dearest friends in the whole United States, I won't name them, but they're professors at prominent universities that are teaching the code. It gives me the heebie-jeebies, because we want kids that come to work for us to have really strong basic technical understanding of element performance and system performance if they get that far in their graduate program. But being able to recite code sections, because they change all the time anyways, so the shelf life on reciting the code is very short. So I'd rather emphasize kind of fundamentals and principles of engineering as opposed to let's recite code language. So anyway, that's my view.
Well, that's a fantastic way to end it, although Ron will be available at the reception, so please again, one more thing, I'm sorry. As the 2021 Sehlin Lecture, I am honored to give you the Certificate of Achievement from the University of Minnesota. Thank you so much.
Thank you, appreciate it, thank you. Thank you.